Hi everyone, this is Mrs. Pullen for lesson 6.10 on the basis of hypothesis testing, specifically for categorical data. And I'm just continuing on. Earlier today we collected some data. We each looked at 5 homes and determined whether or not they were considered to have high lead levels or low level lead levels. If you had more than 15 parts per billion of lead, it was considered high. If it was less than or equal to 15, then it was considered low. I'm using period 7's data since we had more students, so more data. So we found out that 47 homes had high level lead levels and 128 had low lead levels, and that was for a total of 175 homes. So the sample proportion would be 47 out of 175, and I'm going to just enter that quickly into my graphing calculator, and that's approximately 27%. So in the next slide, we're asked to investigate the following case. According to EPA regulations, if more than 10% of homes in a city have high-level lead content in their water, 15 parts per billion, the city's water supply is considered unsafe. Based on your sample your class collected, is there convincing evidence that the water system in Flint is unsafe? So that's what we're investigating. So we're going to use a 4-step process, and step 1 is to define the parameter, state hypotheses, and state the significance level. So the parameter would be rho, and that represents the true proportion of Flint homes with high lead content in their water. Okay, we would then define our null and alternative hypotheses. So they're always stated based on the parameter. Do not use the statistics. Do not use p hat in the statement of your hypotheses. So the null would be p is equal to something, in this case 10%. And the alternative is what you suspect. So we really think that it's greater than 10%. The other thing you need to define in this step is the significance level that you're going to base your decision on, and that's called alpha, Greek letter alpha. It kind of looks like a fish, and you can choose anything, but typically we choose 0.05 or 0.01, sometimes 0.10, but in general 0.05 and 0.01 would be what we would use. So now we're up to step 2, where we state and verify our conditions in order to actually do this test. So, would be a random sample as stated. I know how the data was collected from reading the actual research, and I know that what we did in class was certainly use a random number generator to get our data. The purpose of this condition, again, is so we can generalize the information to the population, and it's not just the population, it's the population of interest. In this case, homeowners in Flint, Michigan. Okay, so now we're up to the second condition. So number 2 is, it is reasonable to assume that there are more than, and again, take your sample size and multiply it by 10, 1,750 homes in Flint, Michigan. It turns out that there are approximately 40,000. The purpose of this condition is so we can sample without replacement. So it's okay, and that we don't break the independence condition, because the sample size is so much smaller than the actual population, so it's really not going to have much of an effect. And the third condition is the large count condition, but be careful. And what I'm saying, be careful, is in this condition, it's important that you use the right P. You are to use, when you're dealing with hypothesis testing, the population proportion, P, not like the confidence interval that you use P hat. Why do you use P and not P hat? Look at what is defined in the null hypothesis. This is what we're assuming to be true. So since we define in our null hypothesis what our rho is, our true population proportion is, that's what you have to use in your success failure condition. If you use P hat, you would be absolutely incorrect and lose points. We notice that both conditions match, and because they match, it allows us, match greater than or equal to 10. Because we met that condition, it allows us to approximate the sampling distribution with a normal model. So that's really important. You now have to provide a summary statement which names the test. Since conditions have been met, we can perform or conduct a one proportion z-test. Notice we're not constructing a confidence interval. We're going to be performing a test. And you have to name that test. This is called a one proportion z-test. So now we are up to step 3, where we actually do the calculations. The general formula they give you in the reference sheet is the test statistic is equal to the statistic minus the parameter over the standard error. Specifically, for a one proportion z-test, the test statistic is called z. The statistic we're using in this formula will be P hat. The parameter is P. And the standard error, you once again would go to the formula sheet, but here again, you have to be careful. When we do the standard error, there is no hats when you're dealing with hypothesis testing. It is simply the parameter. Why do we use the parameter? Because it's defined again in our null hypothesis. So specifically, we would fill in 0.27, the test statistic, minus 0.10, our null hypothesis, what was defined, our parameter as defined in our null hypothesis. Remember again, we're using the parameter in our standard error times Q, which is 0.9, over our sample size, which is 175. And we enter that in, and when we do, we get this really large test statistic of 7.43. That means that you're 7.43 standard deviations above the mean. That's pretty far away, okay? So we're going to use that test statistic in order to calculate our p-value. So we're going to draw our typical bell curve. And we'll label with the parameter and the p-hat first. So this is our parameter, and this is our test statistic. Our parameter was 0.1. Actually, maybe I'll write this the other way. So this is 0.1, and this was our test statistic of 0.27. And this again is p, and this is p hat. And we're calculating, let's get out the highlighter, and we're calculating the p-value, which is this area over here. So in order to calculate the p-value is the probability that we get this test statistic, that's our evidence, and our test statistic was 0.7. What's the probability I got that test statistic, or more extreme, greater than that, so 0.27, assuming that our null hypothesis is true, assuming that the true proportion is 10%. because the mean of this normal distribution, if you recall from the earlier chapter, the mean of the sampling distribution is equal to whatever that population proportion is. So assuming that our mean is true, that our population is true of 0.10, what's the chance that I could have gotten this test statistic just by chance, just by, just random behavior? That's what you're calculating. That's what the p-value is. So where does the test statistic fit in? Well, using p-hat, that test statistic is really just a z-score. So we're converting this notation and we're saying, hey, this is equivalent to the probability that our z-score, our test statistic, is greater than 7.43. So now I can apply a normal model. Z is 7.43, right? So we're going to calculate that area under the normal curve. The low is now that test statistic. Don't use 0.27, use the 7.43, the z-score. The high is 9E999. The mean of a distribution once you use the z-score is 0, and the standard deviation is 1. And when I enter it in the calculator, I get this really, really small number. So this is the notation that would be displayed in your graphing calculator. This is, in scientific notation, 5.47 times 10 to the negative 14. So there are like 13 zeros before the 5. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then you have 5, 4, 7. By the way, you can leave it in scientific notation. I don't need to count zeros. This is like really, really, really small. So basically, what is this saying? This is saying the chance, assuming that 10% is the true proportion, the chance that you could have gotten a sample proportion of 27 is like practically nil. So that means there has to be something wrong with your original null hypothesis. You shouldn't be able to get that value. It would be highly unlikely. So we're going to go on to our last step, step 4, which is where we interpret our p-value and drawing conclusions. So what is our p-value? So this is actually the calculation of the p-value, this whole statement. And so this would be the interpretation. Assuming HO is true, in other words, rho is equal to 10%, there is a 5.47 times 10 to the negative 14. That's where you would enter your p-value. So this is the same for everything. This is the same. Getting a sample proportion, in our case our test statistic was 0.27 or greater, purely by chance. Really, really small. So that meant, again, that something wrong with the null hypothesis, and so this is the conclusion you would make. Since the p-value of 5.47 times 10 to the negative 14th is less than 0.05, we would reject HO. So as long as the p-value is less than the significance level you choose, you would reject it. And then you make a statement, there is convincing evidence that Flint's home water is unsafe. Okay? And we'll be going over more hypothesis testing tomorrow. Have a great evening.